dear colleagues and participants of our online public lecture series, Sustainability in Computer Science. I have heard I didn't read myself yesterday, also last weekend, in the Salzburger Nachrichten, one of the more serious newspapers in Austria. One of our speakers of this lecture series, Professor Ivona Brandic, had an article about, how much energy is used when you ask ChatGPT how to cook your meal, for example. Philipp is laughing, so perhaps you have seen it. So I think this is really, and also this is what our kind of international speaker last week, whoever have attended her, or perhaps you can also kind of look at her presentation, of course, online, Michaela Zint. In fact, what she also told us is one of the most important things now is really awareness building, that we are aware what we do when we do something, like, asking for whatever information. And I know it becomes difficult. In former times we asked, Dr. Google. And nowadays you have to, when you ask Dr. Google, you immediately get an AI-generated answer, and I don't know how much energy has been used in the background. But yeah, therefore we are here. I've just today had a discussion about the so-called in German Gesamtösterreichischer Universitätenplan, which means there is one kind of a framework how all public universities in Austria should kind of be steered, which they should follow. And of course, sustainability is one of the goals in this in this paper. So I think we are at the right time, at the right place with our online public lecture series, and I'm very happy and grateful that Professor Philipp Gschwandtner from the University of Innsbruck has accepted the invitation to provide his insights on high-performance computing in a sustainable way, paving the way for sustainable supercomputing, as he phrases it. Without further ado, Philipp, it's your floor, and we are very much looking forward to your presentation.
Thank you very much. So just a small note, I actually haven't read this article that you mentioned in the Salzburger Nachrichten, but I know the kind of comparison because as I hope most of us are aware, asking these AI tools for advice on cooking recipes or whatever it is takes quite some energy. So I don't have this specific example on my slides, but I hope people are aware of the impact, and we will face this more gravely down the road. I have some hints on that in my slides also here. But today's talk centers a little bit more around HPC in general, with AI being a specific use case for HPC, I guess you could call it. In general, my talk is about green HPC. So the question is, what's green and what's HPC, obviously. So in general, we try to be environmentally friendly. And as you will see throughout my talk, that hits us quite heavily with HPC because HPC has such high environmental demands and requirements. So on the left, we see one of the use cases for HPC. That's an oil spill that happened in 2010 in the Gulf of Mexico or Gulf of America, depending on who you ask. And we collaborated with IBM on improving a simulation application that's able to predict oil spill and oil movements across the ocean. And next to it, there's an AI-generated image. That was one of the example images from ChatGPT like 2 years ago or something, when I asked, what's green HPC about? And you have a plant growing out of a PCB, out of a main board. Doesn't make any sense, but that's what AI sometimes delivers us. I still think it's kind of pretty, so I put it there. And on the right side, obviously, yeah, high performance computing, which doesn't really have an exact definition because it just means we are using supercomputers and compute clusters to solve advanced computation problems that exceed the computational performance of a small consumer device, for example. There is no exact definition for HPC because progress and development are so fast. If we came up with a number today, it would be obsolete in 6 months from now. So it wouldn't make any sense. Generally, I like to consider everything HPC, where I spend a major portion of my brain power not on what I'm doing, but how am I doing it? How do I use the compute resources? How do I use the energy resources? And so on and so on. And two examples here are, for example, the landing gear of a Boeing 777, I believe it was, and the air turbulence created by it, because there's very narrow requirements on how to design those things. So they have just the right amount of air resistance in order to slow down the plane enough, but not too much. And on the right side, we see a space weather prediction illustration where solar particles, charged particles from our sun, hit the Earth and are deflected by the electromagnetic field. We saw this as northern lights just a couple of days ago, I think, right? Even in Austria. And there's lots of simulation going on here in order to figure out how well we need to protect our spacecraft, for example, and satellites and so on. So there's lots of use cases for HPC. But the main sustainability concern really is energy. Even though when closing my lecture today, I will talk about a couple of other aspects, but the main concern is energy. But why is this the case? In order to motivate this, I have a couple of example numbers. So say, for example, you want to charge your smartphone and just it happens to be an iPhone 17, just to give some example. It has a battery capacity of approximately 3.7 amp hours. And if you have 30 cents per kilowatt hour tariff, which is probably about normal in Austria, could in some regions maybe be on the bit expensive side, then charging your phone once a day will in total per year accumulate to about 5 kilowatt hours, which means €1.05, which is quite cheap, to be honest. I was surprised about this number. Sometimes people go like, I'm charging my cell phone at work, so I'm saving money at home. Yes, you are, but you're saving like €1. I'm not sure it's worth thinking about this. Um, if you move down the road, let's turn to our personal computers. If you have a new PC with the current Intel or AMD multi-core processor and a sort of a decent GPU, and let's assume you run it for 4 hours per day. For me, that's not gonna make it by far. My PC is on probably 20 hours a day. But still, if you assume 4 hours per day of game time, for example, if it was a game PC, that would accumulate to 200 kilowatt hours or €60 per year, which already means here it kind of makes sense to turn off the PC if you really don't need it, right? And at the far end of personal power or energy consumption, let's turn to electric vehicles. For example, Skoda Enyaq RS, which is about average to on the large side regarding the battery size, 79 kilowatt hours of battery, and according to the manufacturer, needs 14.2 kilowatt hours per 100 kilometers. I'm not sure if that's actually achievable because that's actually quite efficient, but let's give them the benefit of the doubt. Let's assume it's doable. And you're driving the car for 15,000 kilometers per year, which is also a little bit on the high side, but sort of average. Then this amounts to 2,130 kilowatt hours per year or €640 of charging fees if we charge at home, for example, at the 30 cents per kilowatt hour. So this is already something where I think, okay, I'm not driving around if I don't need to, or if I have solar power, I'm going to use it, and so on and so on. So this is about the maximum in terms of, yeah, ballpark numbers in terms of money, financial resources that we personally care about. Now, coming back to the topic, what about HPC here? The main sustainability concern is HPC's energy because they need so much power. As an example, the largest and fastest system worldwide today is El Capitan in the Livermore National Lab in California in the US, and it's extreme by any measures. It has 11 million cores, adding both CPU and GPU cores, 5 petabytes of main memory, 1.3 exabytes of planned storage. I didn't actually look up the current number that was actually implemented, but in the beginning they planned for more than 1 exabyte. And it's one of the few systems worldwide that manages more than 1 exaflop of peak performance when computing linear algebra. That's 10 to the power of 18 arithmetic operations per second, which is just absurd. But the other number that's absurd is the power draw. In order to do this performance, in order to deliver this performance, it needs 30 megawatts of power. Coming back to our original computation, running this full power the entire year would mean 262 gigawatt hours of energy or almost 80 million euros per year, just keeping the lights on, so to speak. Um, Obviously, they have special tariffs and special contracts with suppliers of energy. So I'm pretty sure they're not paying 80 million, but it's definitely something that you need to consider. And this is one of the reasons, not just the money required, but also the 30 megawatts themselves, why it's one of the main limiting design factors when building these systems. So we could build them larger in terms of floor space. We could build them larger in terms of convincing politics, investing the money, and so on. But how much energy we can pump into the thing and how much heat we can extract out of the thing is really the main design limiting factor here. So 30 megawatts of power, when I heard the number first, really didn't mean much to me. So I thought about doing a small comparison. How much is that actually? Well, 30 megawatts is obviously exactly the amount of energy or power that you need in order to operate the El Capitan supercomputer. It also happens to be just 80% of the Aurora supercomputer, which is number 3 worldwide, which is interesting because it's a system that's slower but needs more power because it's less energy efficient. As a hint, El Capitan uses AMD processors and Aurora is using Intel processors, and they're not as power efficient, at least at the moment. Um, it's also 41% of the energy consumption of the city of Innsbruck and its surrounding villages, which I found rather interesting because Innsbruck has around 120, 130,000 inhabitants. So that means if you put 2 El Capitan supercomputers, it's the same energy consumption as the entire city for over 100,000 people, which sort of also puts things into perspective, I would say. It's 9 times the energy demand of our university, the University of Innsbruck, and only 4.5 times the energy draw of the University of Vienna. I just posted those two here because that's where I could actually find, yeah, energy figures for, which shows that the University of Vienna is twice as large as the University of Innsbruck, at least when it comes to, the energy demands of lab equipment and the like. But you see, these things really consume a lot of power, and we really need to worry about how to deal with properly and how to motivate this properly. How can we make sure that we use those devices responsibly and optimize for energy and so on? One of the big issues we have these days, especially, is AI and the growing need for data centers and computation. And there are lots of predictions and extrapolations out there that show that the current growth of data center sizes, performance demands, and the implied energy consumption and power consumption, this is not maintainable. If we take a look at the left figure, it shows a projection for the upcoming years in the relative portion of energy consumption for data centers in the US, reaching between 7 and 12% until 2028, which is only 2 years away. So then the prediction started in 2023. And on the right side, we see the same, but only for the state of Virginia, which just happens to have a lot of data centers on its, ground. So in 2030, they predict up to almost 50% of energy just going into data centers. Half of the entire energy of the state that's available to them, to the infrastructure. If we continue this, and you can also see the shape here of the lines, which is like worst case and best case scenario, this is not linear growth. This is definitely super linear growth. So there's a couple of figures that show by 2040 or 2050, 90% of the energy draw would go into HPC centers and go into AI. This is not sustainable, obviously. So that's definitely where we need to figure something out. Or maybe the AI bubble will have burst by then. I'm waiting for that to happen every day now, but let's see. But we need to do something about this, obviously, both in making these devices more efficient, but also more responsible use of these devices, not just, using them for any kind of question, but only for the things where it really makes sense. How do we get all of those numbers? Well, in order to gauge how much they need, in order to optimize for energy consumption, we need to measure the data first, obviously. So what you need is you need some power or energy instrumentation. And we see a couple of devices on the right here, an industrial grade power meter. Those devices are pretty expensive. They cost at least a couple of €1,000, but deliver quite accurate numbers. And also some homemade or self-made systems on the right. You can try this at home, but you have to be careful. The lower picture, for example, I saw first in a workshop, I think in Hamburg in 2014 or something, where researchers wanted to measure the energy draw or the power draw rather of their main board, and they had to order a replacement 2 weeks after that because the main board went up in fire because they connected the wires in the wrong way. So when you do energy or power measurements on the server level, you really have to be careful and know what you're doing. So be careful about this. Modern supercomputers have most of this built in already. And there's also a plethora of power or energy models that try to simply predict, dependent on the current use of the system, what the power and energy consumption is going to be. Some are better, some are worse, but for those of you who have dealt with models before, it's just the same story for any kind of use case or any kind of domain, I would say. There's also a lot of metrics out there. I'm only giving two examples here. One of the ones that's used to gauge the data centers, how efficient they are, is the PUE, the power usage effectiveness. That basically means how much energy does the IT equipment need in comparison to how much energy do I pump into the entire facility. And ideally speaking, you're aiming for a PUE of 1. So the entire energy going into the building is only going into the HPC system, and we don't need any additional infrastructure. But realistically speaking, we are at a PUE of 1.05 or 1.1 even for the worst systems maybe, because you need some cooling infrastructure, you need sometimes even heating infrastructure, office space, lighting, and so on and so on. But we're trying to get this as far down to 1 as possible to make sure we're not wasting any energy that could be spent on the HPC system itself. And the second metric is more a metric for the users, which is the energy delay product. Because as soon as you start to optimize for energy, the question is, what about the time? How long do I have to wait? Because that was the original objective that everybody optimized for. People want to have the results of the application as fast as possible. Now that we add energy, we need to combine those two somehow into a single objective, unless you're doing multi-objective optimization. And the EDP, the energy delay product, is simply multiplying energy by wall time and trying to minimize this value in order to keep things nice and easy and keep them single objective, which is much easier from a math perspective. Um, this is not just relevant for us researchers, in our smaller universities and at home maybe, but this is also relevant for the very large systems. So there's the top 500 list that lists the fastest 500 supercomputers worldwide. It's released twice a year in June and November. And what they do is just benchmark all of the systems worldwide with HPL, a high performance LinPack, which is just linear algebra, a bunch of matrix multiplications, LU decomposition, and so on and so on. And then they do a ranking. Yeah, what's the fastest system? What's the second fastest system? And so on. I don't want to get into the details of these exact systems, but I want to direct your vision to the rightmost column, which shows the power draw of these systems, and they're entered into the official top 500 list. It's not mandatory, so we see system number 5, the Eagle system in the United States, doesn't have any numbers. Most likely because they're not very good, because if you had nice energy consumption numbers, you would probably publish them. But so it's also a little bit of marketing as always. But we see, for example, El Capitan, 30 megawatts, as I mentioned before, Aurora number 3, which is almost 40 megawatts, Jupiter Booster, which is a new system from Nordrhein-Westfalen, Germany, so the Jülich Supercomputing Center, with 13 kilowatts of power draw, which is really not a lot, 13 megawatts, sorry. So we see that these numbers are already important, but there's a second list, the Green 500, which puts much more emphasis on that and ranks systems dependent on how energy efficient they are. And I could go a lot into the metrics, how the energy and power values are derived. I'm not going to talk about this because there's 33 pages of definition on that, which can be quite dry or theoretical. But we see that what they compute is the energy efficiency in gigaflops per watts. So how many floating point operations can we do per power spent, per watt that was spent? And that's interesting. But what's also interesting is if we compare the ranks, we see in the first column the ranks of the systems. So the most energy efficient system, second most energy efficient system, and so on. And next to it, we see the ranks of these systems in the top 500 list that just ranks according to performance. So we see the most energy efficient system worldwide in France, in Toulouse, is actually only the 420th when it comes to performance. which already shows this multi-objective trade-off. So you can either go for an energy efficient system or you can go for a fast system. But the fastest system will not be the most energy efficient and vice versa. The topmost we have in this top four that I have here is the second one that manages rank 171, which is still a far cry from position one, right? From being in pole position. So that shows that there is a trade-off involved. You can't have it both ways. Another nice thing that you can do with these data is to give projections on how energy efficiency has progressed throughout the years. So what you see here is data from the top 500 in the Green 500 list from 2008 to 2021 in November. And we see the numbers for the number one system in the Green 500 and the number one system in the top 500. What's the projected power draw if we were to scale this system, this specific system, up to 1 exaflop of performance? How much power would we need to operate it? And we see in the beginning, we would exceed 1000 megawatts, which is not operable by any means because we don't have the infrastructure. But every now and then we manage to increase the energy efficiency and go down to what in 2021 were 34 megawatts for an exaflop, a hypothetical exaflop system. So we see the hypothetical exaflop system always decreased its power draw. And the current system that we have with El Capitan even manages quite more than 1 exaflop at 30 megawatts, which is less than this measurement here. But the publication was published in 2021, so that's the most recent data we had back then. Which shows that we are really improving. We're trying to make it more energy efficient. Obviously, not just for sustainability, but also for economics, because it's a huge amount of financial resources to power these things and yeah, keep the lights on. With all of this data, this opens several avenues of optimization now. So first of all, we can try to make HPC more energy efficient by increasing parallelism. We had to do this in the past already. I have a historic overview slide on the next slide. We do a lot of research in cooling because cooling plays a big factor in how energy efficient the system is. And obviously also the selection of hardware, whether we should use GPUs, for example. And when we work then with energy efficient HPC, it's always a multi-objective problem because you can't optimize for both speed and energy efficiency most of the time because they're conflicting objectives. And then you end up with math problems like Pareto optimality, for example, where you do random sampling or you have some genetic differential evolution algorithms or something similar, where you try to run sophisticated optimizers and migrate your problem space towards this Pareto set where you optimize for both objectives, but you always end up with multiple configurations. So none of these points here in the Pareto set will dominate any of the other points in all objectives. There's always one that's better, for example, in time, but worse in energy. And there's another one that's better in energy, but it's going to be worse in time. And then the user needs to select what he or she is going to do in the end. Whether you want your results really fast and you're able to spend the additional amount of energy, or whether you say, okay, time is not a critical factor, but I'm going to power down my system and make it very energy efficient in order not to waste our planet's resources. Something similar was already done in the past because that's how parallel computing actually came to be. So here we see microprocessor trend data throughout the last 50 years where we have columns of markers, and each column represents one representative CPU architecture of the day, dating back to the 1970s. And what you see is the black dots here, the diamonds, are always a constant line centering around a single core, a single computing core, so no parallelism at all, until around 2005. And around the same time, we see that the power consumption, the power draw, sort of increased, but flattened off almost. And also the frequency increased until around 2000, 2005, and then also flattened off. The reason being because of physical limitations, we cannot build CPUs that run at a higher clock rate than we do today. That's the reason we don't have 15 gigahertz CPUs, because we can't build them and we can't power them properly. It's too much of a hassle to do. So people opted for sticking to the maximum frequency of, at the moment, it tops out at around 5 gigahertz or so, but increasing the number of cores and trying to make them more energy efficient to not increase the power draw too much. The power figures are still increasing a little bit, or it did increase starting 2005, but not as much that it's really an issue. Note that the y-axis is on a logarithmic scale here. So another way to reduce energy is using accelerators. So the accelerator market has been steadily increasing and will likely continue to do so because accelerators are extremely efficient when you run them for the correct use cases. People always say you should port the applications to GPUs because GPUs are much faster at computing stuff. But it only works for the right use cases. Not every use case can be ported properly. So there's still a lot. I would say 90% of what we do in HPC probably has an efficient GPU implementation. And for this reason, the share of accelerators in HPC systems has continued to increase. I only drew this data up to 2021, but at the moment, I think 50% of the top 500 systems are using GPUs or some other form of accelerator because they're much more energy efficient. And you can also see this when you do some data analysis. Here you see data from the top 500 in terms of energy efficiency, so how many gigaflops per watt you get. And we see that there are systems that are not using, so this is based on accelerator type. I'm distinguishing here what kind of accelerator we have in the system. There's a couple of systems that have no accelerator at all, and most of them barely reach 7 gigaflops per watt. A couple of them exceeds it, but those are special ARM-based chips most of the time. And then we have two other clusters, one here and one here, which are notably above the average of those systems. Those are using Tesla V100 GPUs from NVIDIA, and those are using A100 GPUs, which are a newer generation, so the energy efficiency is higher here. I don't have recent data for the new Grace Hopper chips, which are much more energy efficient still, and they would probably rank somewhere up here in the 35 or 40 gigaflops per watt range. But I don't have this data. I should update this figure at some point to get this. And there are also not that many systems that already operate on Grace Hopper because they're quite expensive and they've only been around for 2 or 3 years now. So what can we do? We can reduce energy in computing by tuning software. This is what I did a lot in my research days, trying to make software more energy efficient without changing anything in the hardware. One of the things that you can try to do, for example, is play around with compiler flags or compare different compilers. So I did some research on the IBM Power 7 CPU, which is now already over 10 years old, but it featured some really nice power and energy instrumentation back in the day. And I compared what's going to happen when I'm compiling just the standard suite of benchmarks compiled with the GCC compiler or IBM's own compiler, which probably should be optimized for IBM's own CPU. And the interesting thing was that IBM in general produces more efficient binaries, but not always. We had a couple of benchmarks where GCC, a third-party compiler, not coming from the same company, so to speak, that makes the CPU, manages to compile the application in such a way that it's 30% more energy efficient compared to the binary coming out of IBM's own compiler for the same IBM's own CPU, so to speak. I found this quite surprising. And another thing you can do is you can say, okay, I'm not touching the software, but I'm changing the hardware and I'm playing around with clock frequencies. So here you see a figure of clock frequencies of the Intel SoC, which was an experimental chip in 2011. That's quite a long time ago. But I'm just showing this figure because I have it available and because it allowed a lot of frequency settings. What you see here is what's the energy efficiency of a specific benchmark that I'm running, and the most energy efficient setting. So I'm showing this on the x-axis for multiple frequency settings, going from 100 megahertz to 800 megahertz. And the important thing here is the most energy efficient setting is neither the minimum nor the maximum, but some sweet spot in between. In this case, it's 320 megahertz. You will see this behavior for most of our computing chips these days, where most of the time CPUs, but also applies to GPUs, where the most energy efficient setting is not the minimum or the maximum, but something in between, and it is dependent on the application that you're running. So it's not a fixed setting that you determine once per hardware and then you just run it like that all the time. It depends on the kind of application that you're running. More specifically, how compute bound or how memory bound, for example, it is. So that's also something you can do, but you need to get this data first, obviously. Another cool thing that you can do, no pun intended, is experiment with different cooling infrastructure technologies. And that's where Vienna really shines with its VSC3 system, which is a comparatively old technology these days because it used to be the fastest supercomputer in Austria in 2014 and ranked number 85 on the worldwide list back then. In terms of raw numbers, computing performance, and so on, it was nice in Austria, but internationally speaking, not that impressive. It had 32,000 cores, power draw of 450 kilowatts, okay, but it had a specific PUE value, so power usage effectiveness, of just 1.02, which means basically just 2% of the power going into the thing was not used for actually doing computations, which back then was really, really, really efficient. A lot of systems didn't manage to get anywhere close to this value. So what did they do? They used oil cooling, immersive cooling. What you see here on the right is a photograph of these tanks, which are literally tanks with oil inside, and you have all of the compute nodes lowered vertically into the oil. So in the left, you see one of the tanks that's emptied out for presentation reasons, filled almost up, fully up to the limit with oil. That's non-conductive, obviously. And we see one example compute node here. That's like one full VSC node. That's like it has the same capabilities as your PC at home, just runs much faster. But other than that, it's basically the same in terms of CPU, memory, mainboard, local disk, power supply, and so on. And on the right, we see two of those that are vertically lowered into the oil, and we just see basically the surface of the oil beneath the ports, so we can still connect cables to it. Because that's immersive cooling and you have the normal convection of oil when it's heated up, you saved a lot of energy for fans, for ventilation, for pumps that you don't need for these systems. So that was the reason why the system was really, really efficient. There's also a lot of war stories why they are never going to do anything like that again, because it's an absolute pain in the neck to work with. If we have time at the end of the lecture, maybe I can give a couple of examples. But people are not going to do this again on a widespread scale, even if it is the most energy efficient solution that we probably know of now. It's not worth the effort and maintenance overhead. But it was quite nice that Austria was one of the few sites or countries where something like this was actually implemented in production. More modern systems basically just use water cooling. That's the state-of-the-art technology these days. A computing node will look like this, where almost everything is covered in copper and piping. And we have two hose connections here. One is an inlet and the other one is an outlet where we pump water in, flowing through the entire system, all the pipes, cooling both the CPUs here on the left and four GPUs here on the right, for example, and then flowing back out. And the limits here are fairly high. We see here, for example, on the right, it's a little bit small and I don't have my presenter that allows me to zoom in. But we see here star-shaped indicators with numbers in them that show you the order in which the screws of the cooling plates have to be tightened. So there's four screws and they need to be installed in a very specific order. And here at the bottom, barely readable probably across the live stream, is the torque, which means 1.4 to 1.6 Newton meters, which is the amount of torque that you are allowed to use or need to use in order to tighten the screws. If you tighten them too little, there might be water leakage or something, or not enough cooling contact. If you tighten them too much, you might break the hardware, or again, there is physical tension that again worsens the cooling contact. So this just shows how tight tolerances are when it comes to cooling, because if you do cooling wrong, it doesn't necessarily mean that your system's going to break, but maybe it runs less energy efficient. And if you do this on a large scale, where on a system that costs 50 or 100 million euros, for example, it's really an important factor. And here I have a figure that simply shows the cooling flow through one of the Lenovo nodes. That was from the SuperMUX system in the Leibniz Rechenzentrum in Garching next to Munich in Germany. We see here the inlet going through the memory modules, going through CPUs. It's a little bit of a different architecture than the previous image, and then cooling power supply units and flowing back out through the outflow. And yeah, that's pretty much it. Because of this efficiency, water cooling is also the widespreadest technology, so to speak, the most widespread technology when it comes to an overview of cooling technologies. So there was a survey done in 2020 among the fastest systems just in Europe, and across all of those, 40% of the system used water cooling with warm water cooling. Warm water cooling meaning they don't need to actively cool the water back down. They just do free air cooling on the roof of the building, for example, just some ventilation, a radiator, and it's going to cool down. Then there's cold water cooling, which means you do the same, but on the roof, you need active chilling. You need to actively cool down the water using the same process that is in place in your fridge, for example. So essentially using a heat pump to remove the heat from the water flow. These work very well, the systems, but they are less energy efficient. So they're only used for warmer climates where the free air cooling doesn't work because the ambient temperature reaches 45 degrees, for example. And there's only 10% of the systems using air cooling because air cooling is very easy to build. It's just extremely inefficient because we usually use air to insulate things, right? We don't use it to transport air. We just do it for our laptops and for our PCs and so on because it's convenient to implement, not because it's efficient, right? It's just maintenance efficient, so to speak, and cost efficient. But physically speaking, it's actually a bad choice to do. And a couple of other technologies like indirect cooling or two-phase cooling that, at least in HPC so far, are not really relevant. So I'm not going to go into too much detail about those. Another thing that we can do is recycle the heat that is produced by the system. So a lot of data centers do this already, where they have an inflow temperature for the cooling water of 60 degrees, for example, an outflow temperature of 65 degrees. And then the 65-degree water is definitely hot enough to pump it through a heat exchanger and heat office space, for example. So there's lots of data centers that are built next to lakes or rivers where they get a free supply, so to speak, of cool water, cool their systems. Then the hot water is used to heat the office buildings, sometimes using floor heating, which has very low requirements. You can already operate floor heating just with 35 degrees Celsius water, for example. And then when it's cooled down far enough, you can put it back into the river or the lake with also specific regulations so you don't bother wildlife too much, for example. That's one of the reasons why the Leo 5 supercomputer, which so far was the fastest of the University of Innsbruck, is not connected to the in-river compared to the rest of the building because it would increase the backflow temperature going back into the in-river and affecting fish life too much, unfortunately. So that's where we need to be sustainable in the sense of we're not able to use, the free energy removal of the river because we need to protect our environment just in a different form. So it's a quite complicated topic. But there's lots of countries and lots of sites that do this because it just saves on heating energy. So why not do it? And another aspect is also the general question whether we do sustainability in HPC, which is what I've been talking about so far. How do we make high performance computing more energy efficient, more sustainable, because it has such big demands, such high demands? But also, what about HPC for sustainability? We can use HPC to improve sustainability of our society. I could give countless examples here. I guess most of you are aware of what I'm hinting at, but just two power generators, for example, to make them as efficient as possible, getting the most energy out of wind energy and convert it into electricity. I think for physics reasons, they top out at actually 30% efficiency, if I remember correctly. If you try to draw out more than 30% of wind energy, the wind stops and your turbine stops spinning. So it's a problem. But getting those to be easily built, finding the right sites for them, doing wind parks, for example, also on ocean sites and so on, which is a big topic because there's lots of wind in some certain locations. There's a lot of simulation and modeling going on here. And the lower figure shows a car crash simulation and the stresses that are exerted on the material, on the steel, which improves sustainability because 50 years ago, if you built a new car model or designed a new car model rather, you had to build 50 models, 50 real-sized cars and crash them into a wall at different angles, different directions, crash them into other cars and so on, and then see what happens and whether they're safe for driving. And these days, you do probably 95% of these analyses in HPC, using HPC in order to simulate all of that. And only the best configurations that are protecting lives the best, that are the cheapest to build also, because it's always about economics as well. only those models are then really built, and some of them, some samples are really again driven into the wall to do these NCAP crash tests and so on. But it saves on sustainability because I don't have to build something that I know I'm going to deliberately destroy afterwards again, right? It's the life cycle of resources and materials which we can save here. And the same holds for countless other examples, whether it's drug design or the solar winds example that I showed, which gives us hints on how much we need to protect our spacecraft, because every piece of protection that we need to add to spacecraft adds weight. And if we add more weight, we need to add more fuel in order to send it up to the same orbit as before. That's plain physics, right? So all of this helps us in figuring this out. All of these problems are extremely computationally heavy, and so we need HPC in order to solve these problems. But it's not all fun and games. Not everything is perfect, obviously. So there's lots of open issues. Um, I only or almost only talked about energy and power. And that's not the only sustainability problem, obviously. There's lots of other metrics like carbon usage effectiveness, water usage effectiveness, or space usage effectiveness, for example. And all of them might be applied to your HPC system. And some of the HPC systems that have really nice PUEs for power might really turn out to be really bad in some of these other metrics. The general problem is just there are too many metrics. There's the power usage effectiveness, okay. There's also a partial PUE if you don't want to measure or maybe cannot measure your entire system. There's the energy reuse effectiveness, there's energy reuse factor, which are two different numbers. And all of these metrics are flawed in a certain kind of way. And all of these metrics are used in marketing because you measure all of them for your system, you select the best metric, and that's the one that you're going to publish, obviously, because that's how people work. The PUE, for example, is flawed because it doesn't take into account how you need to cool down in terms of the ambient temperature. So you cannot use it to compare HPC sites between very cold sites in northern Scandinavia, for example, and southern HPC sites in southern Italy, for example. They have two completely different environments, so their PUEs are not directly comparable, so it's an unfair comparison. And as always with humans involved, there are diverging interests. So there's the operators that want to minimize power and energy. They want to maximize workload throughput. There's the user that just wants to get the results as fast as possible. If we, as researchers at universities, run our applications on HPC centers, we really don't care how much energy they consume, right? So most of the time, people just interested in having the results as fast as possible because we don't pay for the electricity ourselves, which is a bad attitude, to be honest. And the taxpayer and politicians just want to minimize overall costs and probably get reelected because of that. So it's always diverging interests. What are current development and ideas? Well, a trend that has been going on for a couple of years already is high bandwidth memory and stacked memory. So as it turns out, computing is one contributor to the energy consumption in HPC systems, but another one is actually moving the data from the memory modules, for example, to the CPU where the actual computation happens. So we try to reduce this as much as possible and put memory and computation units as close together physically as possible in order to literally minimize the physical distance on the chip they need to travel, because that needs energy and that also needs time. In terms of the signal propagation, we are already down to the limit of the speed of electricity. So basically light speed in copper or whatever they're using, which is probably about 2/3 of the speed of light or something. So the only thing we can do in order to reduce latency and reduce energy here is make them, appear on the chip as close together as possible or on the main board. The next thing that will probably happen is near memory computing and memory as compute, which means we are computing directly in the memory chips. It's no longer the case that we have separate memory chips and separate computing chips and we have some interface between them, but it's actually the same chip, the same device that does the thing, both storing the information and computing with it, because then data doesn't need to be moved anymore. We just need to figure out how to do it efficiently. We don't know it yet, but there's a lot of research going on in this direction. Then there's the reduction, in fabrication size, which just means like the nanometers. How small can we build the chips? Because decreasing those also decreases the energy draw and allows us to put more transistors on the same real estate, on the same area. And there's always special purpose hardware, like using accelerators, using FPGAs, building your own custom hardware, which is the most energy efficient solution, but it's also extremely expensive. Just building a handful of chips can cost €1 billion, depending on what you're going for. And there's some nice research proposals like using optical computing, for example. If we could use chips based on photons instead of electrons, they might have much lower energy dissipation and therefore be much cheaper to operate. Maybe we could run CPUs at 20 gigahertz in that case. There's a lot of approaches in research. It's not clear if it's really a viable alternative, but it's nice to see people doing research in this area. And the last bit of information I want to give, and sort of a mind game, at least for me, is situated in physics, but for me, it already turns somehow into philosophy because I'm not a physicist. There is a lower theoretical limit, which is called the Landauer limit, to energy consumption of computation. So how little energy consumption can be when we compute the result of an addition, for example. Why is this the case? Because we have irreversible computation. So if you do some computation, a logical AND of two bits. So we have bit 0 and bit 1. We do an AND operation, and we end up with the result being 0. By doing this operation, we actually erase the information because we don't know the state of the two bits in the beginning. We only know the result. It could have been that both of the bits were 0, or it could have been that only one of those two bits were 1. We only know that definitely not both of them were 1. That's the only information we have at the end. Because we erased information, we must have increased the entropy in our system because apparently that's how thermodynamics work. And there's a lower limit to how much energy you can dissipate, which apparently is 0.0175 electron volts or 2.8 times 10 to the power of minus 21 joules at room temperature. And we're several orders of magnitude away from that. So the Landauer limit itself doesn't bother us really at the moment. The problem is there's also something called Kumi's law, which means that the number of computations that we can do per joule doubles every 1.6 years. So every 1.6 years, we are twice as energy efficient, so to speak, which is similar to Moore's law that says every 2 years, roughly, our systems get twice as fast. If we couple this with Landauer's limit, that means energy efficiency cannot increase any further by 2080. If we manage to keep our current track of increasing energy efficiency, and we probably won't be able to, but still, if we were able to, that means after 2080, chips would no longer be any more energy efficient. We basically hit the limit of physics. And depending on your technology, depending on how you do quantum computing, this also applies to quantum computing. So how do we solve this? Well, one of the reasons we got into this problem is because we had irreversible computing, because we erased information. So the idea is simply do reversible computing, only do operations that do not erase any data. Some technologies, quantum computing, for example, allow you to do this. So if we manage to do that, we might be able to increase further beyond this limit. But since I'm not a physicist, I only understand half of these concepts. Let's see where we're at. Well, in 2080, I'm probably not going to see it, but I still found it a very, very interesting problem. So what's today's takeaway? There's a lot of research and engineering going on in both sustainability within HPC and also HPC for sustainability. So power and heat are the main limiting factors. We could build larger systems in terms of money and space and so on, but we really are hitting the limit of economics and sustainability, how much energy we can get into the device and how much heat we can get back out of the device. Because of that, almost everything uses water cooling these days because it's the sweet spot between what's efficient and what's still maintainable. And the waste heat is often recycled in office buildings and so on, and then freely cooled afterwards, just letting it radiate in fresh air, which we do in Innsbruck, which we also do in Vienna and so on, because that's the most energy efficient solution we know these days. The short-term developments are quite clear, but the long-term future of how to increase sustainability, especially considering the current aspect of AI, is very unclear to me. Let's see where we end up. I have some coordinates here on the slides, which you will have access to because we're also going to publish the PDFs, I think, if I remember correctly. But obviously, I'm also open to any questions you might have right now.
Philipp, thank you very much. I repeat myself. It's all the time, very exciting to look at the numbers and to at least try to understand where we are heading to. So I wait a bit, until the students make up their mind. You said oil cooling was a pain in the neck. Can you give just two, three pointers?
Yes, it's it's the public expression I would use.
Yeah,
If we
yeah,
were talking
no, no,
privately, I would say pain in something else.
yeah,
But
yeah, I
um,
understand.
the problem is that oil is a really maybe I can jump back to
Yeah,
the slide for illustration purposes. Um, Oil is really a pain to work with because we're
yeah,
not used to dealing with it. First of all, it's difficult in terms of maintenance because I'm not sure if this is visible on this photograph here, but you see here we have the normal tiles that are on the
yeah,
floor, and
yeah.
here the floor starts to look somehow differently.
Mhm.
That's because when I visited the VSC3 in 2017 or something, um, they had kitchen towels, paper towels everywhere on the floor because working with oil is so messy, you couldn't stand on the floor anymore. As soon as you spread your feet apart for more than, say, 30 or 40 centimeters, your feet would start to slip apart and you couldn't stand anymore. So, first of all, you would find paper towels on the floor, and second of all, a lot of sand. And I don't know what the English term is for Katzenstreu. So, the kind of sandy substance you would use in cat toilets. It was on the floor everywhere to be able to just walk there normally and do proper maintenance of exchanging cables and stuff. So that's one thing. And this also raises a work safety problem, right? So people working in this room had a higher chance of getting injuries, which is not fun for insurance, I guess. One of the other problems was that I said before that the oil here, the oil surface is actually located below the ports, so you can still connect cables properly and so on. What people didn't realize when they put this up is that oil really creeps everywhere. So
Yeah.
after a couple of weeks or months, they started to have failures in network switches, where the network switches had really strange behavior. And when they checked the network switches, they realized those were actually dripping with oil, clogging the air fans because the network switches were still air cooled. How did this happen? Well, the oil started to creep up the network ports and creeping inside the cables, which apparently nobody thought of before when designing this. And the last example that I have from back then is that it's also a bad choice in terms of hardware procurement because when you want to build one of these large systems, as you probably are aware, you have this bidding process where you come up with a call for HPC system. You come up with, okay, we want to spend 5 million euros. It's so much money and it's taxpayer money. We need to have companies bid and we take the best solution that delivers the best system for the least amount of money, obviously. If we know we want to move to this level of energy efficiency, you end up with oil cooling. That's the only thing that can do it. But submerging these things in oil means you exclude a lot of normal state of the art technologies because they cannot use with oil. Like, for example, if you buy a normal PC or a normal computing node, they all have certain labels on them, which are just paper labels that are printed and then glued onto the chip, onto the PSU, onto the side of the mainboard chassis, and so on and so on. The oil dissolves the glue and makes these paper tags or paper labels flow around and start clogging the pumps and the oil filters that were used, hindering energy efficiency and hindering the cooling. So you need manufacturers that are able to laser engrave serial numbers and specs onto the chips directly instead of using normal papers and glue, which everybody else does. So if you have 10 companies that can build HPC systems in general, if you rely on oil cooling, you only end up with like two of them that can do the laser engraving. So that reduces the cost efficiency of procurement because as a customer, you want as much competition as possible because competition makes it cheaper to build to buy those things, right? So that's the three prime stories I have about why we are probably never going to build anything like that again. It still probably holds the record if we did something like that today with oil cooling. It would be the most energy efficient way of doing it, but it's not worth the effort, not by a long shot.
You were mentioning the Leibniz, yeah,
The Leibniz-Rechenzentrum, yeah?
Rechenzentrum
Yeah,
of compute systems, yeah,
yeah.
a compute center. So now I have the English term. Um, and I remember that they have some green roof where they used the water from the cooling also to, build plants in when it is a bit colder and so on. Um, I don't think that we have this at TU Wien. Is there anything like that in Innsbruck? When you have, you have Musica, you have this connection to the of the kind of classic HPC to the quantum computer. Do you
Um,
are you aware?
no, okay, the connection to HPC and quantum computing is a little bit irrespective of energy because the quantum computers are actually quite energy efficient. The
Mhm,
ones that we have in Innsbruck, coming from AQT, so Alpine Quantum
mhm,
Technologies, and the company of Thomas Montz, um, they are extremely efficient. So if they want to sell a quantum computer, the only thing they need is two server racks, which is like probably 2 or 3 cubic meters of volume, and a
mhm,
2 kilowatt line of electricity, and that's everything you need to operate the quantum computer. So they're extremely energy efficient. The classic HPC systems produce much more waste heat than that. So it's only about interfacing those two in terms of network and collaborating on the same application and so on. Um, but in terms of energy dissipation, only HPC is really the relevant factor here, and we don't have any special. I have one fun story about this with the Leo 5 system, which is the sort of the predecessor to Musica and is
mhm,
the fastest system we had so far in Innsbruck. It's in the CCB building, which also houses chemistry and pharmacy. And they have these cooling devices on the roof, these active chillers, which were specified up to I think 35 or 37 degrees of ambient air temperature. And when they designed this system, they didn't realize how bad climate change was going to be. So after 1 or 2 years, they already hit the operating limit of those cooling devices on the roof. And redoing those would cost a lot of money, like probably millions of euros. So probably they thought about, okay, let's try something simpler, and ended up with just having sort of some Gardena literally hoses that when it's really hot, they turn up the water and spray the cooling radiators with fresh water from the pipe in order to just give you this 5 Celsius degree advantage or something, in order to stay within the operating limit of those cooling devices. So that's a really home-baked solution. It
mhm.
probably cost less than 1,000 euros to implement, and it works quite efficiently. To be honest, I don't know what the water usage is per year, but it's probably not a lot because they only need to shave off a couple of degrees every
Mhm,
year during August, for example.
mhm,
Beyond that, we're currently looking into more sustainable ways of reusing the waste heat, but at
mhm,
the moment it's a little bit difficult because in the sites that we have at the university and also the sites that we're using from the IKB, which is our local energy
mhm,
provider that also provides HPC housing and so on. Um, Ordinarily, you would connect it to the general heating infrastructure, but we don't match temperature levels well enough. So economically speaking, it's not worth doing because you invest more money building the infrastructure in order to meet the temperature goals, and you don't get this money back. And the question is always, okay, sustainability is a good thing, but if it costs 10 times more money to do it, then you're probably still not going to do it because you can't justify the tax expenses to do
yeah.
so. It's always a trade-off for society also. So maybe we're going to do something more fancy in the future, but at the moment we're very classical and conventional in Innsbruck.
So we are in fact kind of entertaining the I guess all the others since nobody has further question.
Yeah.
You were at the beginning you were mentioning of course the AI bubble. Will the AI bubble burst? What do you think? I know this has nothing to do with your as not really immediately with your
Okay.
scientific presentation, but this is something I think we as a, at least as a computer scientist, we should kind of have a mind about that.
First of all, the disclaimer is I'm not giving financial advice, not for anybody. This is not
Okay.
investment advice. But still, having said that, I would say the AI bubble will burst. I'm waiting any day for it to happen now for for two major reasons. The first reason is that if you look, all of these companies like Microsoft, Amazon, Nvidia, OpenAI, and so on, they all have very, very large revenue numbers. The numbers look absolutely astronomical. until you take a look at the larger picture and realize it's basically money and resources traveling around in circles, going from one of those companies to another of those companies, but it's a closed ecosystem. There's really not a lot of interaction with the outside in regard to that. Of course, Nvidia is also selling GPUs to gamers and so on, but if you compare the market share and the amount of money flowing somewhere, AI basically beats everything by 95%. So the biggest part of the revenue is earned by dealing with other companies that you use their platforms and you supply them with hardware. So they're just running around in circles.
Yeah.
And that's always the indicator of a bubble, right? If other markets and if the market doesn't improve by having other companies and other entities jump in and doing more interfacing and more networking. The other reason is that I think AI is doing absolutely fantastic things these days, but there's lots of people building businesses around AI, hoping it will be able to achieve things it cannot achieve at the moment, and I'm not sure it will be able to in the future. So the things that AI can do these days, like whether you go for ChatGPT 5 or Gemini 3 or Opus 4.5 and so on, all of those models are absolutely awesome. And as a computer scientist, you should use them for your work. A tool like a hammer, and you wouldn't nail a nail into the wall using your bare hand. You would use a hammer for that. So these AI systems are tools in order to do that. So please use them. But you have to be aware of the limitations. And I think what they can do today very well, they obviously will continue to do very well tomorrow. But there's a lot of people outside of computer science that are building business cases around these systems, expecting features they don't provide yet, and it's unclear whether they will in the future. And then these business cases will probably crash and companies will go out of business. So a lot of people outside of computer science are just putting expectations into AI that AI might not be able to meet. And this coupled with the fact that we have this closed ecosystem of at most 10 companies in an AI exchanging money and exchanging goods, I think will lead to the AI bubble bursting. But then again, I could be wrong. I don't have my crystal ball with me right now. So who knows what it will look like in a couple of years from now. But I hope, as a personal note, I hope it will crash because hardware prices are just through the roof at the moment. So
Yeah.
main memory modules cost 5 or 6 times the amount of money they cost like 6 months ago or 8 months ago. So some of these hardware prices are just astronomical. And for everybody else, for normal customers, I really hope it will burst soon in order to make personal computers for us affordable again. But yeah, let's see what happens.
Um, Perhaps a last question. Along also this line, now you were mentioning NVIDIA, OpenAI, and so on, and as we know, they are all from North America, so the United States. We are discussing quite a lot about digital sovereignty. Is it
Yep.
possible that Europe, when we start now, and of course it doesn't work until tomorrow and not perhaps within a year, would it be possible that we build up a digital sovereignty in Europe over the next, I don't know, 10 years?
I th would it be possible? I think yes, but
And especially your area, not? High
I
performance computing, and of course,
I think that's sort of a tradition of Europe figuring out, hey, we have to do something and we should build the industry for it and the research and development and everything and the markets, and we figure it out at least 15 years too late. That's
but
that's
it's
to me.
never too late, or?
It's not, yeah, yes and no. I mean, the problem is we started this European processor initiative a couple of years ago, right? And we're pumping billions and billions of euros into this. But what people, I don't know, maybe in 30 years from now, we will think this was a really good idea to start it in 2020 or 2015 or whenever it started. But building your own hardware at this kind of level is extremely difficult. That's why we have a couple of plants of fabs that can do this that are mostly located in Taiwan. And a lot of countries like China or the US would like to build their own, but technology is so extreme. There's a very good, if I can do some advertisement, there's a very good YouTube video on that from the Veritasium channel, which is sort of a physics documentary channel on the company ASML, which is a Dutch company that builds the machines that then build computing chips. And the physical conditions you have to meet in order to be able to build those chips they are just absurd. That's why these machines and these companies are so extremely expensive. Just building one of the fabs costs something like 10 billion euros or something. So trying to catch up with other countries, other continents, other companies, of course you can do it in theory, but it might take decades and it takes much more money than some people like to admit. It's probably one of the major reasons why China didn't invade Taiwan yet, because then they're going to destroy all these manufacturing plants, and then there are no computing chips anymore, also not for China, at least not any modern ones or any fast ones. On the other hand, Europe, I think, had a really good track record so far in terms of software and platforming when it comes to using the hardware, making the best of the hardware, optimizing it, and so on. So digital sovereignty when it comes to cloud services and tools, compilers, optimizers, I think we have a really good shot at managing this and becoming independent. And we're already trying to do this right now. There's lots of small bits and aspects and pieces, also in HPC, where Europe starts to become independent when it comes to package managers in HPC, for example. So far, we used to use some US-made solution. Now, these days, our modern systems are actually using a homegrown solution from within the European Union. So in terms of software, I think there's a clear path that we can follow, and we are on track already. In terms of hardware, we are probably as dependent as everybody else, and yeah, it's not necessarily a good thing. So whether we will manage that, I really don't know. Let's see.
Thank you. No further question from my side. Why is quantum computing so
Huh.
efficient? And do you think this will solve some of the HPC efficiency problems?
Yeah. Okay. So first of all, excellent question. I was wondering whether something like this would come up. Why is quantum computing so efficient? Quantum computing is very efficient, but only for a certain class of problems. So there's the computing complexity or theoretical complexity kind of analysis in computer science, which in layman's terms means, is a problem solvable in almost infinite time? If I have like 100 years, could I solve it? Or is it considered to be so complex that we consider it unsolvable because it would take so long, it wouldn't make any sense to run it on a classical system? And that's where quantum computers can really shine, because they move this problem from a realm where we say it's unsolvable to actually it can be solved in time that actually is manageable by us, in polynomial time, as people call it. So quantum computers are really here to stay, because these kind of problems will never be efficiently, at least to the current state of knowledge, never be efficiently solvable on classical HPC. At the same time, quantum computers will not replace HPC, because there's lots of classic use cases for which a quantum computer is not more efficient, but brings a lot of overhead to use. For example, quantum computers always need a lot of repeated measurements because of uncertainties. And if you do a measurement, you fix, so quantum uncertainty, you always fix the value to either being 0 or 1, even though before it was approximately zero point 0.7 or something. So by measuring, you actually destroy the actual result. How do we get then values between 0 and 1? You have to repeat your measurement and use statistics and see, on average, it probably should be zero point 0.7, because 70% of the time we receive the 1 and 30% of the time we receive the 0. Running these experiments 10,000 times, 100,000 times is more expensive compared to classical chips, where you just run it once because it's deterministic and you end up with the correct result. So something like something like quantum computing will never replace a normal calculator, for example, that you have in your smartphones, because smartphones can do this sufficiently well, I would say, and they don't need a lot of cooling. You don't need to do ion traps or something else that people do these days. So I think it will become more popular and more affordable. It will probably be something like an extension to your normal PC. Like today, we want to buy faster GPUs, so you get a PCI Express card and plug it into your normal PC, because then you get faster graphics performance. Probably in 30, 40, 50 years from now, we will have extension cards to do polynomial solving of Shor's algorithm or something, and we plug our quantum computer into our, not PCI Express slot, but whatever is the successor then, I guess. When this will happen, I have no idea. I'm pretty sure it will happen, because 100 years ago, nobody fathomed the performance we have now in our pockets, basically. But when this will be the case, I have no idea. Is reversible computing the only solution to energy efficiency limits by 2080? How is it achievable? I have no idea. So I would have to lie now, and since I'm a scientist, I try not to do that at least. Um, I'm not even sure that reversible, because reversible computing is a really nice concept on paper. On paper, it solves our problems. That would mean by doing reversible computing, we don't spend any heat, we don't have any entropy increase, right? If you build a quantum computer in hardware these days, you obviously need to cool the thing. So obviously there is something going on with heat. Because we probably know the theory about quantum computing, but we haven't figured out the hardware, how to do it without, all of the supporting infrastructure around it. So I think even if we figure out the theory behind this, it's probably similar to, I don't know, relativity theories coming from Einstein and so on. Einstein figured this out, what, like 100 years ago or something, and still today we go like, this is probably correct, but actually using this in real implementation in real physics is really, really difficult for us. So the same goes for reversible computing probably. Maybe in a couple of years we will have figured everything out, but we don't know how to build it that way actually.
Wow, I think this is a very good statement at the end, yeah, that a very honest statement that there are enough problems to be solved going by its impact on aquatic lives. How efficient is water cooling compared to oil cooling?
A good question. I don't have any precise numbers. If you're interested, you can send me an email and I can try to find some publication for you. It's essentially just because oil is a better heat conductor than water and much better than air, obviously. So that's why we want to use it. But I don't have any precise numbers, to be honest. If you're interested, feel free to drop me an email and I can look up a reference.
Okay. Thank you very much. Thank you for sending the slides as usual, so that we
Will you
can
so?
put them online. For those participants, students online from TU Wien, we will have the seminar work you have to do, all the information online. I see here Marianne Schnellmann, who will provide the information on Tuvel, and I'm pretty sure the other the other locations will also provide their information for their students. If anybody wants to do some kind of grading. In general, this online public lecture series really intends to raise the awareness that especially we as computer scientists and with AI it has become even more important, and that we have to that, as I always say, we are on the one hand solution provider, but we are also the problem maker, so we should
Yes,
perhaps solve our own problems.
exactly, as usual.
As usual. um, yeah, Professor Gschwandtner, Philipp, thank you very much for the presentation, also for the discussion. This was really very, very nice and enlightening, fresh as usual. Thank you to all the participants. And I guess we will come back next year. I think this is one of the nice things what we can do at universities, that we can take this initiative and also work together to. Austria is small enough that we can really include all the different locations where computer science is taught at the universities, and to work together for a better world. When you look in the news every day, you can almost not believe it, but let's believe it. A bit
Yeah,
for a
sometimes I,
better world.
I stop reading the news these days, but very good closing statement. I fully agree with you.
Okay, Philip, thank you very much, and goodbye to everybody.
Thank you, Kati. See you.
See you.
Bye, everybody.